Okay, so last we left off, we were actually talking about the metric system, and we are talking about the metric system. We've also talked about significant figures. Um, so we're going to talk about that conversion between the metric system and the U.S. customary system. So that's what the that's what the USCS stands for, is United States Customary System. So in this case, we're talking about the conversions between um, the metric system and the our standard system. So in the US, we often will use like feet, inches, yards, miles. And with the metric system, you're going to be using uh, centimeters, meters, kilometers, and stuff for length. And so we need to be able to get those conversions. So if you guys picked up the packet or if you downloaded the packet that's on your Canvas shell and modules, it should be under important links. There should be something that's chemical packet. You guys can print that out. You guys are able to use that on the exam. Now, the conversion for length, at the scale that we're typically going to be using or smaller, we're going to be using for the US customary system, it's going to be inches. So 1 inch is going to be approximately equal to 2.54 centimeters. And mass, 1 pound, is going to be equal to 453.59237 grams. For volume, 1 gallon is going to be equal to 3.785411784 liters. And as we know, with the customary system, 1 foot is going to be equal to 12 inches. 1 yard is going to be 3 feet. 1 mile is going to be 5,280 feet. 1 pound, 16 ounces. 1 quart is 32 fluid ounces. 1 gallon is 4 quarts. So here's an example. A soft drink manufacturer is converting from the United States customary system units to the metric units. If the quart bottle initially is to remain the same volume, what number of milliliters should be printed on the label? Now, when we do this, we always want to start off with what's given to us, right? So in this case, what's given to us? And you guys can respond by typing, or you can respond by unmuting yourself and talking, you know? And again, we want to make sure that you guys are interacting. So try to interact. It'll make it a little bit better. It'll also make me feel like I'm not talking to a black screen. So, or I'm crazy, one or the other. Okay, so what do you guys think is going to be our starting point or our starting unit that we're going to be starting off?
Does it start with quarts?
Quarts, that's right. So I'm going to start off with 1 quart. Okay, so what do we know about the quart that could help us get to milliliters? Because that's our goal. We want to get to milliliters. So how many quarts are in a gallon?
There's 4 quarts in 1 gallon.
Okay, so we have 4 quarts in 1 gallon. So because we have quarts on top, to get rid of quarts, we want to put quarts on the bottom. And then we're going to put 1 gallon. Okay, so I'm going to put over here on the side, we said 4 quarts equal 1 gallon. And so we use gal for gallon. Okay, so if we look at our units here, as I said, by putting them on top of each other. So right now, this line here is going to represent division. The line, I'll make it a color. 1 second. See if I can work this out. So this line right here is going to represent division, and then these lines will represent multiplication. Okay, so we have gallon. We want to get to milliliters. So we should probably get to liters first. So what is the conversion for gallons to liters? So the abbreviation for liters is L.
Is it 3.78541178 to
That's right. So
again?
we're going to be a little lazy, and so we're going to go 3.785, right? And if I remember, it's 7854. Is that correct? Or was it 78?
It was 3.7854.
Okay.
Uh-huh.
So since that 4 would be that next number, we're just going to leave it at 5 because 4 is less than 5. So we're going to not round up just to make our lives a little bit easier. And so this is going to be liter. This is going to be gallon. Wait, 1 gallon is equal to, sorry, I messed that up. 1 gallon is equal to liters, 3.7854 liters. There we go. Okay, so then we're going to use that. So again, we have gallons on top. So then we're going to put gallons on the bottom so that we can get rid of that. So you guys know that the reason why we do that is that if we had X over X, what would that equal?
1?
1. Okay, so if I have gallons over gallons, that's also going to be equal to 1. Okay. And are you guys seeing my closed caption? Is that coming up on your end?
Yes.
Good. Okay. So we're going to go ahead and put that 1 gallon. And then the 3.785 liters on top. So again, your gallons are going to be able to cancel out. Our quarts have canceled out. And so now technically, if we do everything, we would be left with just liters. So how many milliliters are there in 1 liter? Anybody speak Spanish?
So there are 1,000 milliliters in 1 liter?
Correct. So mil means 1,000, doesn't it?
Yes.
I mean, I said right. I'm working on it. I'm working on my Spanish there. So we know that 1 liter is going to be 1,000 milliliters. So now we're going to also use that. So I'm going to ask you guys, since I have liters on top right now, so where should I put the liters? Should they be on top or on bottom?
I think they go on the bottom, right? So that
That is
they can
correct.
cancel out.
Yep. Okay, so then what we're going to do, we're going to multiply across. So 1 times 1 times 3.785 times 1,000. And then we're going to divide that by 4, right? And then we had 4 times 1 times 1. So if you guys do that math, what do you guys end up?
I got 946.25.
Okay. $946.25. Now, the question is, if we were doing significant figures, right, for this problem, how many sig figs would we have? Now, the thing is that we started off with a whole number, right? Usually a whole number is considered to be an exact number. 1 quart would be considered to be an exact number, unless they said 1.0 quarts. So that's kind of like saying 1.0000000. So in this case, we are not going to have to worry about the sig figs. So it would be okay just to do it. And when you're doing conversions, your conversion factors, those aren't going to be taken into consideration for your significant figures. Okay? So that would be the answer. Pretty straightforward. Yes, no, maybe. Any questions? Okay, great. No questions. That means we can start moving forward. But I'm going to also give you a quick analogy. I like this analogy because it's easy for me to remember. So, how many of you guys date or have a significant other, boyfriend or girlfriend or a husband or
I do.
okay? Anyone else? Or had? You may not have one now, but you may have had one in the past. You can raise up your hand or okay. Okay, so a couple of you guys have. Okay, good. So now, is your husband the only man that you dated, or has there been anybody else? I'm getting all in your business. Don't take it, too personal.
No.
No, okay. So there was somebody before him.
Yes.
Okay, so let's talk about this a little bit, right? So if we think about it, let's say you made that transition to your new guy, your new beau, your husband, right? So your old boyfriend, is he a priority in your life?
No.
No, but your husband is, right?
Yes.
Okay, let's hope so, because otherwise there's a lot of other things that are going to be happening. So when you think about it, the one that you want to get with is going to be your priority. The old one you're trying to get rid of, so they're going to be on the bottom. So the one that we're always trying to get rid of is always going to be on the bottom. The one that we're trying to get to is always going to be on top. And so that's a good way of remembering it. It helps us visualize it and it helps us think about it because we always make the one that we want to get with priority. The one that we're dumping, we're always going to put them on the bottom. So like here, quart, we wanted to get rid of it. So we're going to put it on the bottom. Then gallon becomes important. Then we wanted to get rid of gallons. Gallons goes on the bottom. Then liter becomes important. Then we want to get rid of liters. Well, liters get on the bottom, and then milliliters becomes important. Okay? Do you guys see the analogy?
Yes, good analogy.
Okay. And it's important that you guys get this because this is what's you're gonna be doing it from the till the very end of the semester. But the concept of dimensional analysis is always going to be a part of what you do. You can't get rid of it. Okay. Now temperature. So I should also say before we get really knee deep into this, your kits. We should have your kits, or if you don't already have your kits and you have not gotten the code for your kits, we should have those codes by this week. I apologize. There was some confusion that went on and things didn't quite work out the way they're supposed to yet. So we should have the codes any day now. And again, I apologize. We're trying to make it reasonable for you guys so you don't have to pay for the kit itself. But with that, we end up having to go through the logistics on campus, and so there were a lot of delays that happened because there was some miscommunication. So I apologize. We will try to get to them as soon as possible. Until then, we'll be doing a couple of labs. But the ones who've gotten their kits, you guys will be able to. I'll have you guys set up to be able to get started. So, and then there was also little quirks that went on with the modules where they weren't opening up the next module. So we're in the process of getting those fixed. We figured out the problem, and so I just need to fix it for all of the other modules so that they start opening up the way they're supposed to. And the biggest thing was that how it was set up for particularly for the students that don't have their codes yet, they weren't able to move on to the next part. And you weren't able to see the next modules because you hadn't entered your code. So we're going to make some adjustments to try to make sure that you guys are able to get through the course and not get hung up on those little details. I apologize for working out the kinks, trying a couple of new things. Temperature. So Fahrenheit is one of the scales that we're used to. So in the US, we use Fahrenheit. So like when we look at our stove, how much we bake our chicken, just like 350 degrees Fahrenheit. The rest of the world uses the Celsius scale. So because we're in science and we're going to often deal with the US, since we're in the US, and we're also going to be dealing with Celsius since we're going to be often working with people from other countries or other places. Um, so we want to be familiar with how to make those conversions from Celsius to Fahrenheit and Fahrenheit to Celsius. There's also another scale, and I'll talk about it here in a second in a little more detail, but we also have what we call the absolute zero scale, which is the Kelvin scale. And the reason why we choose that scale is because at absolute zero, everything stops moving. So that means molecules will stop moving at absolute zero. And so that is the scale that we typically use in chemistry and in some of the other sciences. You may also have heard of the scale called Rankine. Those are often used in the US for engineering. That's an absolute zero scale for it's another absolute zero scale. And it's slightly different than the one that we use because it's based upon the Fahrenheit scale rather than the Celsius scale. And again, we'll talk about that in detail. So this here is the equation to to convert from Fahrenheit to Celsius. And so the way the equation is set up, we're trying to get Celsius. So that's why T Celsius is over here. And then we're starting off with T Fahrenheit. So the equation is real simple. T Fahrenheit, temperature in Fahrenheit, minus 32 divided by 1.8. 1.8 is also 9 divided by 5. So you'll often see it that way, written that way as well. Let me pull up something. Okay, so this is the chemical packet that I was making reference to. So you guys should probably download it because it has conversion for you. So here, this is the periodic table. You can also go to P table. Here's conversions. So let me flip this. Okay, so you can see here that we have various conversions. So we have liters, pints, quarts, and gallons. So we know 4 quarts is equal to 1 gallon. So you see the 1.00. So this will allow us to do a lot of those conversions that we're used to. Here's an example of going from grams to centigrams to milligrams. So we know that the base is grams, and then centi would be the prefixes to let us know how small it is. And so these are very, familiar to us as well. We want to keep track of those. They'll help us figure those things out. And then here, this represents volume. Volume is often referred to as capacity, right? And when we talk about volume, volume is the space that is being occupied. And also, if I go too fast, I was listening to the video of myself. I get very excited because I like what I do. And so sometimes I will put it in fourth and fifth gear. And so if I'm going too fast, slow me down because I like to talk. So the other thing is I have this one as well. Same thing. There we go. Okay, so here, if you look over on this side right here, this has all of the steps, right? And it actually gives you a nice little explanation of how to use it. So I made photocopies of this is because, you know, often we'll have to Google it or look it up. Here you have it all in a single packet. And again, you can use this packet on your exam where you can't do that for Google. They also have units of measurements to help us remember what this kilo, centi, milli, micro means. So that'll help us with some other things as well too. Um, we also have Avogadro's number here. So, which is actually technically off because it's 6.022, and then it goes there. So it's missing a two after before that. And then there's the ideal gas. So there's a couple of things that help us out. And then there's other things in the packet that we'll talk about a little bit. So I wanted to share that with you. And that packet is on uh, Canvas under modules. And then you can also find it in the lab. Or you'll be able to find it in the lab app as well. So I'll be uploading it there for you too. So, okay. So let's go ahead and see if we can work this out. We're also going to talk about, as I said, absolute zero scale, which is the Kelvin scale. So absolute zero is 0 degrees Kelvin, which is going to be equivalent to minus 273.15 degrees Celsius. So this would be the conversion to go from Celsius to Kelvin. So if we put zero in there, so we know that then if we have 0 degrees Celsius, that's going to be 273.15 degrees Kelvin. And this is just basically saying what I said. And that's the point where 0 degrees Celsius is where water freezes. And water boils at 100 degrees. That's right. Okay. So what I'd like you guys to do, I would like you guys to convert the temperature that water freezes to Fahrenheit. So degrees Fahrenheit, and then Kelvin. Okay. So I'll give you guys a minute or two to get started, or a couple minutes, and then we'll do it together. Okay. So if we go ahead and solve for our Fahrenheit value, we're going to go ahead and put 0 in for our TC. So then TF is going to be equal to so in this case, we're putting 0 in there, so it's 1.8 times 0 plus 32. Okay, so what is 1.8 times 0? 1.8 times 0.
So is it 32?
The answer should be 32. Yes, at the end. So 1.8 times 0 plus 32 is just going to be 32. That is correct. So if we do the same thing for 100, so in this case, we have 1.8 times 100 plus 32. Julian, are you going to help us out with this? Okay,
212?
that is correct. 112. Okay, so if we're going to do, and we want to put our units, so we want to make sure we put degrees Fahrenheit. Otherwise, we don't know what we're talking about. Okay, now Kelvin. So in this case, this is our temperature in Celsius. So we're just going to plug it into this value right here. So we have 0 plus 273. They dropped the 0.15. It's normally there. A lot of times you'll have it included. Sometimes you don't. So in that case, the answer is going to be just 273. And then that's going to be, and then in the case of 100, 100 plus 273. So what is 100 plus 273? That's right. 373. Okay. Pretty straightforward. Not too bad. Okay. So again, the more you use it, you'll start remembering some of the equations and stuff. And so it gets easier the more you do it. Okay. Did everybody get everything down before I move on to the next slide? Okay, good. Okay, so this is just comparing both, I mean, all three scales. Um, so this is our Fahrenheit scale, this is our Celsius scale, this is our absolute zero scale. And so you can see that we verified our numbers. So we're pretty good at doing that math. So most of us know that body temperature is 98.6 degrees Fahrenheit. Um, so that's going to be equivalent to 37 degrees Celsius. So are you guys familiar with Saccharomyces cerevisiae or yeast? So Saccharomyces cerevisiae is brewing yeast. Um, they're used to make beer or make alcohol, wine. Uh, their perfect temperature is 37 degrees Celsius. And so there's other yeast which are pathogens, right? Their perfect temperature are also the same temperature, like Candida albicans. Candida albicans is like, say, if you have a yeast infection, that's the one that causes yeast infection. Or if you have thrush, you get a lot of buildup and pussy gums and stuff like that. That's Candida albicans. So the thing is that our body is like the perfect incubator for like yeast cells and bacteria cells. And so those are like the ideal places for pathogens to grow. Most of you guys are planning to go into nursing, just some extra stuff. So in the old days, um, because we would often have fevers that are associated with bacterial infections, because they're trying to make you prime for doing what they want to do, and plus your body's trying to fight them back. So your body has a tendency of increasing its temperature when it's trying to fight off those pathogens. Because 37 is ideal. As you start going up, it actually starts killing some of those pathogens. But others of those pathogens love that extra heat, or they can live within that range. So what would be done in a lot of cases is that they would actually drop your temperature. And initially, because that slows those pathogens in their growth. And then so they would try to do that to sit there and slow that growth. So then that way your treatment would actually have time to catch up with the bacteria. So let's convert 288 Kelvin to its Fahrenheit scale equivalent. And let me give you a hint. You're going to have to go through Celsius, then you have to go to Kelvin. I mean, to Fahrenheit. So we're going to be 288 Kelvin. So we know the change from Kelvin to Celsius. So TK was equal to TC plus 273. So now we want to go to get to TC. And then that's just going to be TK minus 273. Okay, so we'll go ahead and plug in that number. So we have 288 minus 273. And that's going to be 15 degrees Celsius. Okay. So now we have it in Celsius. So if I want to go from Celsius to Fahrenheit, We had that earlier. TF is going to be equal to 1.8 times TC.
Is it
Right.
59?
32. Did you say 9?
I said 59.
59. Okay. Yeah.
Oh wait, no. I added instead of subtracting.
Finish.
No, you should be adding, actually. That's my bad. So it should be a plus. It shouldn't be a subtraction. So you got 59 degrees Fahrenheit. Good job. Okay, questions? No questions? Anybody want to give me $1 million? And if you don't answer, that means that you really do. So I'll just start crediting it to you guys. Okay, man, I'm going to be rich. I'll start sending you the bills. Okay. For each temperature given in the table, calculate the equivalent temperature in the other scales. I'll give you guys some time. And we'll compare that to the answers now. And like I said, ask me questions because otherwise we can finish, 2 chapters in a single sitting. Okay. So you guys ready? What did you get for minus 25 degrees Celsius? And we're converting to Fahrenheit.
I got negative 13.
Okay. Negative 13. Get a different. Okay. What about Kelvin?
I got 248.
Okay. Okay. What about Celsius? From 105 Fahrenheit.
I wasn't sure. I think it's 73. I wasn't sure which formula to use.
Okay. So it's not 73. So
Okay.
the formula that you're going to be using, since we're going from Fahrenheit to Celsius, is going to be the one that's listed right here. So let's go ahead and do that. So we go ahead and plug in 105 minus 32. And we're going to divide that by 1.8.
Oh, I forgot to divide it.
Ah, and so we end up with 41. Okay. And what about 105 Fahrenheit to Kelvin? So we can kind of use this number and plug it in for Kelvin. up here. That's right, Chantel. So it'll be 314. Okay, so now we're going from 364 Kelvin to Celsius. So in this case, we're going to be using this equation here. So Kelvin is 364. And then so we're going to just subtract that 273. What did you guys end up with? That's right, 91. Okay, and Fahrenheit. So now that we have it in Celsius, it'll be easier for us to do it in Fahrenheit, or we could use this. That is wrong. See, I screw up. Actually, this is incorrect. This part here. So, it's 32. That should be. Sorry, this here should be 4, 8, 9.4. Oh, 1.8 times 64. I still got that wrong for some reason.
The formula that you're looking at, it has Kelvin, but we're doing Celsius to Kelvin.
Yeah, let me fix that.
I mean, we're doing Celsius to Fahrenheit. I mean, that's what it is. So I think it's 1.8 times C. Is it plus 32? I think it's that one, right?
It's this one if we're going, if
Yeah,
we're
it's
going,
that one. Yeah. So
yeah.
then
We
it's
should be able to,
195.8, right? Or 196.
So you should be able to also go directly from Kelvin to Fahrenheit by putting in this equation in for your TC. So then in this case, it'll be 1.8 times TK minus 459 instead of 489.4. 364 times 1.8 minus 459. Yep, that's it. Okay. And so that last number is going to be approximately 196. Okay. So these are the equations that you guys can use. And then this is actually going straight from Kelvin to Fahrenheit. So you may want to actually write that if you guys have your packet, you may want to write that at the top of your packet as well, or write it somewhere so you can write it on your packet when you print your packet. Speaking of your packets, I have put 5 packets at the Lemoore campus in the ACE tutoring center. It's right next to the computer that you have to sign in. And so I put 5 packets there. If there are no packets there and you happen to be on the Lemoore campus and you guys want a packet, then let me know and I'll just drop off some more there. I put 5 packets in the Mesa Center at the Coalinga campus. And then I put 5 packets at Fireball Center on the in the library. Those students from Soledad, you guys, you've already have the packet because I handed those out to you guys in lab. So any questions so far? Good. Okay, so often we will be looking at chemical changes. And so when we talk about those chemical changes, we're talking about um, our final temperature minus our initial temperature. So our delta T, and you'll see this often, means change. Delta means change, so the change in temperature. We're going to be looking at the temperature final minus temperature initial. So determine the change in temperature when water drops from 32 degrees Celsius to 6 degrees Celsius.
Can you go back to that last slide? I'm sorry, I didn't get to write it down. Thank you.
And under modules, you should have the packets themselves. So each of the packets that I have, they're listed in the modules. So it'll say lecture notes. And so these packets will be available there. So like if you guys have a tablet or something like that, you like using a tablet, you can take notes on your tablet. Or if you like paper copies, because I love paper. So determine the change in temperature when water drops from 32 degrees Celsius to 6 degrees Celsius. Now, I'm also going to say this because often we have to pay attention to our units. So if we have Celsius, but we really need to get Fahrenheit based upon the equation that we're working with, we would need to make that conversion first, because otherwise, to go to Fahrenheit to Celsius is going to be a little different, right? Because it's not based upon factors of multiplication. There's also something that I have to subtract as well. So we want to make sure to do our conversion before we go and do the subtraction. So in this case, we don't have to worry about it. So 32 minus 6.
26.
Okay, so it's 26 degrees Celsius. Okay, straightforward, not too bad, right? Okay, so often we'll be talking about proportionality. So if we say things are directly proportional, so that basically means that as one thing goes up, the other thing also has to go up, right? So they're going to increase in value, both of them, right? So if we say something is directly proportional to each other, if we say something is indirectly proportional or inversely proportional, that means as one goes up, the other one goes down. That's one goes up, the other one is going to go down. Okay. And so often it kind of gives us an idea of our quantity. So if we pay attention to what we're doing, we should kind of get an idea of whether things are going to go up or kind of go down, depending on what's there. So let me give you an example. So So P stands for pressure, V stands for volume. So pressure times volume is going to be equal to a constant or a value of work. Okay. So K is going to represent this constant. Now, since these guys are being multiplied by each other, we can also write the equation as P, and actually I should do this to be P over 1 over V times K. Or we could just say K divided by V. But I'm going to write it like this to make it a little bit easier for us to understand. Okay, so as pressure goes up, our volume is always going to go down so that we can get that constant. So let me give you an example. So if we have a number, we're going to say our constant is 1 to be simple. So if our constant is equal to 1, constant K is going to be equal to 1. So as pressure, and then this is going to be volume. So as pressure increases, pressure is 1, then our volume is 1, right? Because 1 times 1 is going to equal 1. If pressure is 2, then what is going to be our volume? So what does our volume have to be if pressure is 2?
Is it 2? Because K is 1?
Well, if K is 1,
Well,
so you're
wait.
saying 2 times 2 is 1? Is that true? Based upon our equation here?
Oh, no. I was thinking 2 times 1.
Yeah. So we know it would have to be a half because we want to get 1, right? So because 2 times 1 over 2, that's always going to be a half. So it's going to be a half, right? So then in this case, is going to be 1/2. Okay, so our volume is going to be 1/2. So if volume is is 2, then pressure is going to be, so for it to be 1, what does it have to be? What does our pressure have to be? So let's do it like this. K, we know that K is going to be equal to P times V, right? And if we know volume is going to be 2, what is P going to be if K is always going to be 1? So what, 2 times what will equal 1? Okay, let's do it like this. If you have $2, right, and we want to get to $1, what do I need to do? So I think I'm going to go to your guys' house and take your money. Anybody there?
Wait, what was that? I was
I said
thinking half, but
half. That's right. That is correct. It's half, right? Because if we had $2 and we want to get it to 1, you take half of it, right? That would give me my 1. So you're right. It's a half. Okay. So if we look at it, so pressure, if we go look at pressure, when pressure is a half, it's 2, right? Volume is 2. When pressure is 1, then volume is 1, right? When pressure is 2, then volume is a half. So as we go up, I should probably put this in order to make it look easier to understand. So let's do that real quick. Okay, so as pressure increases, it starts off as a half, then it goes down to 1. So volume starts off at 2, then it goes to 1. Then volume goes to, pressure goes to 2, then volume goes to a half. So as pressure increases, volume decreases. As volume increases, pressure decreases. So that would be inversely proportional. Do you guys see that? And so that kind of helps us understand when we have things that are being multiplied by each other, they're on the same side being multiplied by each other, they're going to be indirectly proportional or inversely proportional. Because one goes up, the other one has to go down to maintain that value. Okay. When things are divided by each other, so in that case, we'd have, say, density. Density is going to be mass over volume. Okay, so density is considered to be a constant. It changes with temperature, but for the most part, if you are always at the room temperature, always at the same temperature, your density is always going to be a constant. So, like for instance, the density of water is approximately 1. So, and it's going to be 1 gram per milliliter. Okay, so if we're talking about the density of water, we're going to assume that it's going to be 1. Okay, so we have 1 gram per milliliter. And then that's going to be equal to the mass of water over the volume of water. And then we're just going to put H2O for water. Okay, so if I have 50 mils, which is our volume, then what must be my mass? So that it equals 1. So what 50 divided by, or I should say, my volume is 50. So the mass has to be what for it to be 1?
50?
50. So that would be 50 grams. Okay. Now, if my volume is 100, then my mass must be what? So that it equals 1.
100?
Okay. And if my mass is 1,000, my volume has to be what? So that it equals 1,000 grams. Ugh. 1,000, that's right. So it'd be 1,000 milliliters. So if we look at the trend, as volume increased, what happened to the mass? Did it increase or decrease? Jinxie, what do you think? That's right, it increased. Okay. And so that shows that it's directly proportional. So a lot of times we're going to be working with equations that are going to either be directly proportional, they're going to increase as the other one increase, or they're going to be indirectly proportional or inversely proportional. One will increase, the other one will be decreased. And so um, you need to be paying attention to that. So if they're multiplied by each other, such as our volume times our pressure earlier, right? They're on the same side being multiplied by each other, they're going to be inversely proportional. If they're divided by each other, then they're going to be directly proportional. Okay. Okay, so here, this is just basically showing you what we talked about. So mass and volume are proportional to each other, so they're directly proportional to each other. So by putting that density, that constant there, we're able to say that they're equal to each other. Okay. Okay. So we will be using density quite a bit. It's one of the properties of chemical compounds or solutions or liquids. So, so in this case, when we make reference to our density, we often will be talking about grams per milliliter or mass over volume, where grams is a mass and milliliters is a volume. Or we'll be talking about grams over centimeters cubed, which is equivalent to 1 liter or 1 milliliter, sorry, 1 milliliter. Okay. Density, like I told you, is going to be dependent on temperature. So it's going to change because the volume changes as the temperature changes. So have you guys ever had a soda in a hot in a very hot weather and that soda bowed? Did you guys ever has that ever happened to you guys where the bottle deforms a little bit and you can't sit it down on its bottom because you left it in the car too long?
Yes.
Yes. Okay. So we're all kind of familiar with that. And that's because the volume expanded and it causes the plastic to move. Okay. So uh, these are basically particulates view of solids of 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 solid and liquid water. So here we have ice, and then here we have uh, we have liquid. So ice, it actually is very organized, but when it organizes itself, it kind of expands a little bit. So have you ever anybody put soda or a bottle of water or something like that in the freezer, and you notice that it deformed, the bottle deformed in that case too?
Yes.
Yeah. Or like a Coke can and left it in there, or a beer. I used to leave my beer in the freezer all the time and they pop open and stuff. Hot mess. But anyway, so it's because it organizes itself and it puts a little pocket of air, right? And because of that pocket of air in the ice, that's also going to cause the ice to be less dense than the water, right? It also causes it to take up a little more space. So when it freezes, it organizes, but it takes up more space compared to when it's in the liquid form where it just kind of interacts with each other. So we know that ice floats, and and then this is the case. This is a solid ethanol. So ethanol is drinking alcohol. So if you freeze drinking alcohol, it'll actually drop to the bottom. Um, and then of liquid alcohol because it's heavier, it's more dense than the liquid itself. Where ice is lighter than the liquid itself because it puts those air pockets in there. Okay. So things float when it's less dense, things sink when it's more dense. Okay. So boats, why do boats float? Wooden boats specifically, or a piece of wood. Why do wood float on water?
The density is less than water.
That's right. So we know that wood is going to be less dense than water. It has a lot more air that's able to get through it. So lumber floats. So pine, maple, oak, they all float. Why do helium balloons float?
Their density.
Their density, right? Helium is less dense than air. You can see that here. So helium is 0.00717. Air is 0.0012. Air is more dense than helium, so helium will float in air. So the mass of 50 mils sample of methanol is 39.59 grams. Determine the density. So what is the equation for density? So if you remember, density is going to be mass divided by volume. So what is the mass in this case? That's right, 39.59 grams. And then the volume is the 50.00
Oh.
milliliters. Okay, so 39.59 grams divided by 50 milliliters. Now here we need to pay attention to significant figures. So the fact that we put this decimal point here, these zeros are going to be significant, and also this zero is going to be significant. So in this case, we have 4 significant figures. Here we have 39.59, right? So those are all non-zero numbers. So in this case, all 4 numbers are going to be significant. So when we do divisions or multiplication, it's always going to be the one that's the smallest. In this case, they're both the same, so they're both 4. So we should end up with an answer that has 4 significant figures. And so we end up with 0.7918. And we want to make sure to include our units. It will be grams per milliliter. You guys have to excuse my 3rd grade handwriting. Okay, questions? Okay. And so we always want to make sure that we're putting our units because that helps me understand what you've done and what you're talking about. Because a lot of times we'll get an answer and I'm like, what is this answer for? Okay. Okay, the next question. Oh, everybody was good? Or did I need to go back? Because I do get carried away. Are there any questions? Okay. Next question. So the density of a certain machine oil is 0.910 grams per milliliter. Find the volume occupied by 196 grams of that oil. Okay, so we know the equation of density. So we're just going to use D for density. And of course, it's M for mass and V for volume. So here, what are we given? What's given to us in this equation? I mean, in this question. What do we?
0.910 grams per milliliter.
And that's is it the mass, the volume, or the density? No,
That's the density?
That is the density because it tells us the density of a certain machine oil is 0.910, and it's also grams per milliliter. So we know that the unit for density is always going to be grams per milliliter or grams per cubic centimeters or pounds per gallons. So that would always be density, right? So we have our D, right? So we're going to go put that on our D side. And the units are grams per milliliter. Okay, and then it says find the volume. So we're looking for V. That's what we don't know, but we're given the mass. So we just rearrange our equation to get V by itself. So we're going to get V is going to be equal to, so this is going to be brought underneath. So we have 196, and let me put those units, which are grams, divided by 0.910. That would be grams. And then since these grams are on the bottom here, when we bring it underneath, it becomes those milliliters are going to come on top. So then grams are going to cancel out, and we're going to be left with just milliliters. So 196 divided by 0.190
I got 215.384615
Okay.
at significant figures. Is it
So,
3?
so 215, you said 215.38.
8.
Yeah, so we'll leave it 38, and the units should be milliliters, right? So, and you said how many sig figs?
Oh,
Significant.
I think I had said 3, but
Three. That is correct, right? Because here we have the decimal. So that means that everything here is going to be significant. All those following are going to be significant. So that's 1, 2, 3 there. And you also had 1, 2, 3. So both cases, there are 3. We know our sig figs are going to be 3 significant figures. So then the answer should be 215. As we take this 3 and we take a look at it, if it's greater than 5, we round it up. If it's not greater than 5, we just get rid of the rest. Right? So 315 milliliters. Okay, questions? No questions? Everybody got this down? Any questions about significant figures? Because I take off a point for each question that you mess up on your sig figs.
I have a question.
Yes,
So basically, though, for the second problem is that we're just finding the volume basically.
that's correct. Yep, because it
So,
told us what they want us to find. It says find the volume, right? And
mhm.
we know that we're given the density and we're given the mass. So if we're given the density and the mass, we can find the volume.
Um, okay, that's all for now.
Okay.
okay, I have a question about the significant figures.
Okay.
Yeah, okay, so whenever it's like 0 point, like whatever the number is, the numbers after the decimal are the significant figures, or how does?
So it has to be whole numbers, right? So first off, well, I should say non-zero numbers are always going to be significant. And then after that, if you have zeros, it depends on where they're located. So in this case, they're located after the decimal. So you're telling this person, because the way that we want to look at this, we could get away with writing this number as 0.91, right? We don't need that zero, right? But the fact that we put that zero, that tells the reader or tells us, since we're working on it, or another group, that that zero is going to be important. It's significant because we took that extra time to write that zero, right? Because we don't need it, but we put that extra time to let you know that it's there,
Oh,
right?
yeah, that makes sense. Yeah.
Okay, so that would be a significant zero. Now, in this case, let's say we had a number like this, 0.0084, right? So these zeros here, they're not significant. They're just space holders. They let us know the value that we're working with, the fact that this is a really small number, right? So these numbers that are in front wouldn't be significant because they're just letting us know the value. But
Okay.
if we all of a sudden put a zero after it, that would be significant because we don't need it. We're just letting you know this is going to be an important one. So does that make sense?
Yeah, it does. Yeah. Thank you.
And I'm glad you stopped me because a lot of students have trouble with that, but everybody's shy and they don't want to be wrong. Let me tell you, I'm going to make 150 time mistakes because like earlier we made a mistake on when I put minus and I fix it later on. That's always going to happen, right? Nobody's perfect. We're going to make mistakes. And the way that we learn is by us making those mistakes. Has anybody ever been the perfect child? You know, never got in trouble, never did anything wrong,
No.
never peed on the floor, you know?
No,
No,
no.
exactly. Right. So don't expect to be perfect here. I expect you guys to make mistakes. And if you're not making mistakes, you're not trying. Right. And so then that also lets me know something like, oh, you didn't make any mistakes. So something's wrong, huh? And again, stop me because, like I said, I talk very fast. And I just realized that recently because I never really listened to myself. And the worst thing is that my brain is even faster.
As time goes fast, it's really quick. It's like, yeah, it goes really fast.
Yeah, it does. Okay, so the next thing we're going to be talking about is quantity. Okay, are you guys familiar with quantity? How many kids do you guys have? Anybody have kids?
I have 4.
Yeah, 4. Wow. Okay, but that's a lot of kids. I want 6, but you know, all my girlfriends said no, that's not going to happen. So I haven't had one yet. None? Anyone else have kids?
0.
0 kids? 1? Okay. So you got the prize, Juanita, with 4. So
Woo!
we'll get you something. I have a gift card for you. So I should get you 4 since you're probably gonna need 4 times the amount of stuff, for it. So when we talk about
4
quantity,
plus 2 plus the parents.
what was that?
I need 6 because there's 4 plus the parents too. The parents, we were
Oh,
trying to
okay,
get the
that's
4.
true. Okay, I got you. I got you. So when we talk about quantity, we're talking about, the quantity, the number we have, right? So it's going to be numbers that we're going to be talking. So often we're going to be making reference to quantity. So you guys have heard of the dozen before, right? A dozen of kids, a dozen of donuts, a dozen of bagels, right? So what does a dozen represent?
12.
12, okay? And we know that. We know that it's always 12, okay? Now in chemistry, we have something that's kind of equivalent to the dozen. We call it the mole, right? 1 mole. And I know the first thing that you guys think of is that little animal that comes out of the ground. We're not talking about that mole, okay? When we make reference to a mole, the value of a mole is going to be 6.022 times 10 to the 23rd, okay? So every time you think of a mole, you need to think of 6.022 times 10 to the 23rd. And that's going to represent the quantity, right? It's going to represent quantity of something. So if I tell you I have a mole of kids, that means I have 6.022 times 10 to the 23rd kids. And I'm probably broke as hell because that is a lot of kids, right? Or if I say I have 6.022 times 10 to the 23rd girlfriends, I can say I have a mole of girlfriends, right? So it's also like the dozen, but it's a much larger number. Does that make sense?
Yes.
So because we're talking about things, like when we're talking about chemical reactions, this plus this gives us this, right? So we're always going to be talking about quantity. And so it's important for us to understand that the mole is going to represent quantity, but it's going to be a very large number because often we have to play with that quantity with our hands. And a single molecule is going to be so little and so small that we can't hold a single molecule. We're going to have to hold something like 6.022 times 10 to the 23rd molecules for us to be able to play with it and use it for things. Okay. So the mole is going to be amount of substances that contain the same number of units as the number of atoms in 12 grams of carbon 12. So we based the mole on 12 grams of carbon 12. Carbon 12 is a carbon isotope that weighs 12 grams exactly. And so that's kind of like what our scale is based upon. Okay. And so when we talk about 1 mole of substance, we're always making reference to 6.022 times 10 to the 23rd substances, okay, of that substance. Okay. And often we're talking about molecules or atoms or, like I said, it could be girlfriends, it could be shoes, it could be underwear, it could be anything. So 1 mole of anything is just going to be 6.022 times 10 to the. This is also called Avogadro's number. Avogadro's number. Now, often in my class, it's often mistake for avocado's number because it looks kind of like avocado in the spelling. And so a lot of students will say avocado's number, but it's Avogadro's number. Okay. Or they'll call it Avogadro's constant. Okay. Do you have any questions so far? Okay, good. So a sample contains 0.25 moles of ammonia. How many ammonia molecules is that? So we're going to do dimensional analysis. What is our starting point? What's our given? Because we're always going to start with our given.
0.25 mole.
0.25 moles. So the abbreviation for moles, believe it or not, is just going to be MOL. We dropped the E. That's the abbreviation for moles. Okay, and it's of ammonia. I'm going to write the chemical formula for ammonia because I'm going to be a little lazy. So even though we haven't gone over chemical formulas, so you guys are learning your first chemical formula. So this is ammonia. Well, you probably already know your first one. Water was your first one, H2O. So ammonia, NH3. Okay. So we have 0.25 moles. So we know that 1 mole is equal to how many molecules?
Six 6.022 times 10 to the 23rd.
Okay. So we know we're going to put the moles on the bottom. And then we're going to put that number, 6.022 times 10 to the 23rd, on the top. And so this would be molecules. So this one we have to spell out so we don't mistake moles for molecules of ammonia. Okay, so then those moles are going to cancel out. And then we're going to be left with our value. So 0.25 times 6.022 times 10 to the 23rd. That value should be what? And how many sig figs should we have? So it's 1.5 times 10 to the 23rd. So if we actually do this, that's the full thing. Zero, 5, 5 molecules. Oops. And that's of ammonia. Sorry, I ran out of room. Okay. So how many sig figs should I have? How many sig figs are here for this number?
So is it 2 or is it 3?
It's 2.
2? Okay.
So because this only has 2, remember this one is just kind of a placeholder as well, this 0 here.
Okay.
And so if it's after our non-zero numbers, after the decimal and after our non-zero numbers, then that's when it becomes significant. So in this case, the answer should be 1.5 times 10 to the 23rd. And we want to make sure not to forget that 10 to the 23rd. Another common mistake of students that are just starting out.
What does NH3 mean?
That is the chemical formula for ammonia.
Ah,
The N represents nitrogen, the H represents hydrogen, and the 3 tells us how many hydrogen.
okay, thank you.
Well, yes, Chantel, you're correct. There was 2 sig figs. So How are you guys feeling about your first chapter? We finished our very first one. We're a little slow. We're going to get a little bit faster, I promise. Not too bad?
It's
It
okay.
was okay.
So there's the recording from last week and there's this recording. And I have older recordings and I realize some of them have a lot of background noises. And then, of course, they're in class. The reason I choose the ones that are in class is because a lot of times students ask questions that you guys may not ask. And since typically I have maybe one or two people that will ask questions. So we want to try to encourage you guys to ask more questions so that we get those recordings so that it helps the other students. And now I'm in my office, so I don't have as much background noise. So these recordings are going to be even better than the ones that we have. So I'm thinking, so it's what, 8? So we're going to do a little bit of the next slide, but let's take a, we'll say a 10-minute break. Okay. So the study of chemistry is the study of matter. Okay. And that's one thing that we want to try to keep in mind. So we're always talking about the study of matter. We're talking about chemistry. Now, everything has mass associated with it. Now, sometimes we may not be able to measure that mass because we don't have tools that are able to get down to that level. But everything does have a mass that's going to be associated with it. Or we may have tools, but we don't have them personally. So when we talk about matter, we're going to be talking about it in terms of the macroscopic, the microscopic, and the particulate. Macroscopic is basically what we can actually see with our eyes. So it's going to be on the scale that we can actually visualize it, right? So like a sheet of paper or a ring, CD, okay? So that would be macroscopic, okay? Microscopic is going to be what we have to use a light microscope or a classic microscope to visualize. So, we have to use like that to see plant cells or animal cells or bacterial cells. Okay. And then a particulate are going to be so small that you can't see them with a light microscope. You're going to have to use something that is specialized to see them, specialized microscope, like an electron microscope or a scanning tunneling microscope. So in those cases, we're going to have to use those specialized pieces of equipment. So those are going to be things kind of like the virus, a protein molecule, aspirin molecule, water molecule, which is a single water molecule, or an atom. So because in chemistry, we're often working at the particulate level, we often will use a model to represent chemicals, chemical compounds. And so a molecule or a chemical compound are often going to be represented by a ball and stick model, which you can kind of see here. This is a classic ball and stick model shown in this picture here. This is representing the simplistic perception drawing. So this is what we typically draw on a piece of paper to represent. In this case, this is called methane. And the chemical formula for methane, are you guys able to see my screen?
Yes, the one that says model.
Yes.
Yeah.
So this would be the chemical formula. So C stands for carbon, H is for hydrogen, and this lets us know if there's not a number by it, that means that there's one of them. If there's a number by it, that number that's right next to it lets us know the quantity that we have. So this has 4 hydrogens. So this is the way we draw it. This is a compound. It's bonded together. This here is that plastic model of it. This here is the ball and stick model, digital representation. And then this is a space filling model. And then this is all of them kind of drawn on top of each other. So you can kind of see it visually. Okay. And so because we can't visualize it, because they're often so small, we will use models to sit there and help us understand, or we often will just draw the stick figure of it. So. So the letters that we see, they're going to be representing those atoms. So H, like I said, was for a hydrogen atom. O is for an oxygen atom. So when we talk about H2O, that means that we have two hydrogen atoms and we have one oxygen atom. And these are bonded together, right? So they're a unit together. Okay. So when we talk about these molecules or these atoms and things like that, they can exist in three major states. There's technically four, but we're only going to be talking about the three major. So that's going to be a solid, that's going to be a liquid, that's going to be a gas. So if we think about water, when it's in its solid form, we call that what?
Ice.
Ice. We call it water when it's in its liquid form. And then we call it when it's, what do we call it when it's in its gas form?
Wait.
Is it steam or something?
Steam. That's right. We call it steam or we call it vapor, right?
Vapor, yeah.
So those are the three states of water, right? Now, the difference between those three states of water are going to be the fact that in solid form, we have movement, right? It's very, very little movement. In the water form, there's a lot more movement, right? So, like, for instance, here's my water bottle, right?
Oh, you want my thing?
It's moving quite well, right? And then in the case of the gas form, there's even more movement because if we are boiling water, the steam will actually take over the entire room, right? And those are molecules that are moving around that entire room, you know? And so
What?
we have what we call the kinetic molecular theory. And what that basically means is that things are constantly moving. These molecules are moving. And as we go from different states, we get more and more movement, right? So the ice state, we have very little movement going on. In the liquid state, we have a lot more movement. And in the gas state, it's like crazy movement, right? Have any of you guys ever been to a dance club or to a party? Yeah, some of you guys been to a party? Okay, so we've got to work on this, right? So either I'm assuming that none of you guys have ever been to a party. You guys, if that's the case, then you need to get a chance, and you guys should probably have a party with each other because there's enough of you guys to have a really nice party, right? So if you ever go to a dance club or a party, right, when there aren't that many people there, there's a lot of room on the floor. So you're able to sit there and dance and take up, all of the room on the floor and just act crazy and all that stuff. As more and more people come, right, it gets a little more tighter, right? And so you're going to be packed in a little bit more. So if you guys doing that line dance, the Kirby shuffle or the electric slide or anything like that, you can do those things and stuff and still get some movement because everybody's moving the same, right? But as it gets really, really, really packed, you don't have a lot of room to dance, right? And so you're just kind of bopping. So these are kind of like the molecules. So when it's a solid, they're kind of tight together. Everything is really tight. And as we heat them up, they get a little bit looser, right? And so they're able to move a little bit more. And as we heat it up even more, they're able to sit there and move all around, way around. So the kinetic molecular theory is just the concept that things are always in motion, right? Even the solid is going to be in motion. There's movement, but a lot less movement than in the case of the liquid, and a whole lot less than the gas. Okay. And so as temperature increases, the speed is going to increase. Okay. And so that's what the kinetic molecular theory is all about. Okay. So gas particles, they're going to be moving faster than all the rest. They're going to be farther apart. They're going to be able to overcome some of those attractive forces, things that are kind of sticking them together. Liquids, those things, they're going to be touching each other. They're going to be like moving, but they're going to be moving freely together. But they're going to be amongst each other. Whereas solid, you're going to get vibrations. You're going to get barely any movement. So when we talk about solids, there are two types of solids. There are crystalline solids, and I should say major groups. Crystalline solids, and there's amorphous. Crystalline solids, they're going to have order. They're going to have defined patterns. So they're going to be really organized in their structure. Amorphous is going to be lack of pattern. A means lack. Morph means shape. So it's the lack of shape. So when we talk about those states of matter, here we have, let's say at the top, we have gas. So if we're going from a gas to a liquid, that process is called condensation. If we go from a liquid to a gas, that is called vaporization, or it's called boiling. So this here, let me fix this. This is a typo. And I need to fix it for mine. So this here, fusion, this actually should be fusion. So as we go from a liquid to a solid, that's going to be freezing, or it's going to be also called fusion. And as we go from a solid to a liquid, that's melting. Okay. As we go from a solid to a gas, that's called sublimation. As we go from a gas to a solid, that's called deposition. So if you guys can fix that on your slides. Okay, let me go back one more. Yes, family parties always count. Okay, so now when we talk about water, right? And so often we'll have all of those states existing. You'll have some water vapor, which is kind of like steam. You'll have the liquid water, and then sometimes you'll have a solid that's frozen. So particularly like in the Antarctic and stuff. So to move from these different sites, they're going to require energy, either removing energy or putting in energy. And so we're going to be talking quite a bit about energy. But to go from state to state to state, that requires energy. Okay. So these are the three states of matter. This is kind of telling us, the telltale, and it's kind of like a little summary, right? So we have gas, and this here represents our steam. So you can see the molecules are able to move out. They're going to be very far apart. They're going to be moving. These are going to be liquids. So your liquid, they're all going to be contained in that container itself. And here's your solid. That's going to be only in that little cube of ice that we have there. Now, the shape is going to be dependent on our vessel that we're using. So if we have it open to the room, the whole room is going to be filled up with that steam. In the case of the liquid, it's going to be only the bottom of the container that we're in. And the gas, it's going to be rigid, right? So it's just going to be very fixed. So you're going to keep that cube of ice that you have. In the case of volume, so it's going to be the same as the closed container. So if my closed container is a room, then the volume is going to be the full room. In the case of the liquid, it's going to be constant, whatever we have it set at. And then in the case of the gas, it's also going to be constant. Its movement, right? Its movement of a gas is going to be independent. It's going to be random. So things are just going to be flying all over the place, sometimes bouncing off of each other and things to that extent. But it's going to be independent. The water is also going to be independent. And so, but it's going to be limited to the volume of the water and the shape of our container. And then in the case of the solid, it's going to be vibrating in a very fixed position. And then in terms of spacing, they're going to be far apart. In terms of the gas, they're going to be really close. They're going to be interacting with each other in the case of the water. And then they're going to be extremely close in the case of the particulate. Okay. But we also know that in the case of water, it's organized. It puts spaces in between, which allows the ice to float. So in the case of physical properties, often when we make reference to the different states, those are representing the different physical properties. And so as we go from ice and we go from to a liquid, that's going to be the physical change. So if we're changing from one state to another state, that's going to represent physical change. Okay. So when we make reference to physical properties, so those are characteristics that can be observed and measured without altering the identity of the substance. So in other words, if it's water, it's always going to be water, right? So you're not changing the identity of it. You may be changing the. So we know that ice is water. We know that liquid is water. Liquid water is water. And then we also know that steam is water. So, and again, with the physical changes, it's going to be changes that occur in the form of a substance without changing its identity. So now a chemical change is going to be different. Chemical change is going to be the change of the identity. So you're going to either be destroying or making a new substance. And we should kind of be careful with how we say that, because at the end of the day, the substances that are being made or altered, and altered might be a better word rather than destroyed, you're not truly destroying it. You're changing its form. You're changing its identity. So like, for instance, we have sucrose. So the chemical formula for sucrose is C12, H22, and O11. Now, when we heat up sugar, and let's say we're trying to make caramel and stuff, and we overcook it, we'll notice that there's a change that occurs. So we go from the white sucrose sugar that we're used to putting in our cereal or in our coffee, then it'll caramelize. It'll get brown in color and stuff like that. So that's a process of that change that's happening. Now, if we let it cook too long and cook it too high, then what we'll end up seeing, it all turn black. And so what you'll see, you'll get the formation of carbon. So you're basically breaking down the carbon. Carbon is going by itself, and then you're getting water produced. So carbon and water. So in this case, we're going to be making carbon. So we're just going to use a C for carbon and water, which is H2O. Okay. Now, when we're making reference to these chemicals, we also talk about their states. And so we make a reference to the state that they're in. So this sugar, is that a solid, liquid, or gas?
Oh man,
Solid.
It's a solid. So to represent a solid, what we're going to use an S. Now my S's often look like fives, so bear with me. So we're going to use an S. So, and that's going to equal a solid. If it's a liquid, we're going to use L. And if it's a gas, we're going to use G. And if we dissolve it in water, we're going to use AQ for aqueous. Some people say aqueous. Sorry for yawning. It's been a long day. I've been up since 4 this morning. Okay, so we're talking about this chemical formula. So there's a law. This law is called the law of conservation. The law of conservation basically says, it says what you put in, you have to get out. That's the summary, right? Or it says matter can't be created or destroyed. It can be altered, okay? And so in this case, we're altering this sucrose, which is this chemical formula here. It has 12 carbons, it has 22 hydrogens, and it has 11 oxygens. We know that it's going to be making carbon and water. Now, when we look at this chemical formula, I'm going to move this to a whiteboard so that we can play with it a little bit more. Do that real quick without too much hassle. Okay, so we had C12, H22, and O11. Okay, we know that sugar is a solid, so we're going to put an S by it. And then the arrow is called yield. It yields something. That basically means you're making something, right? So we're yielding carbon. That's also going to be a solid. And then in this case, it's steam that's going to be coming off. So then we're going to put H2O, and we're going to put a gas there. So we're going to be balancing chemical equations. So I'm going to show you that real quick. Okay, so if we take a look at this, the way I always like to do this is I write down all of the elements that are in this compound. Now, when we make reference to these elements, an element is it going to be either a single letter, single capital letter, or it's going to be a capital letter with a lowercase letter. So those are your two possibilities. Okay. And if you guys look at your periodic table, let me pull up a periodic table soon. Let's work with this one first, and then we'll pull up a periodic table. So I told you that the C represents carbon. So we're going to put, it has a carbon atom, it has hydrogen, and it has O is for oxygen. So C is for carbon, H is for hydrogen, and O is for oxygen. Now, it's important for us to remember that these are capital letters, because if we use lowercase letters, it's going to be hard for us to figure things out, right? Because like we have things that are uppercase and lowercase. So we want to make sure that we're writing them the correct way. So this tells us this number here is called the subscript. So it's telling us the quantity of that element. So in the case of carbon, how many carbons do we have?
$12.
Yes. Chantel, yes. So there is, this chapter is on paper. So in Mesa, in all of the locations, I put the chapter 2 packet, I put the chapter 3 packet, I put chapter 5 and chapter 11. So you should have 4 different packets that are there, in addition to the chemical packet, if you pick them up. If they aren't there, let's say you're on campus, right? So don't go unless you're on campus. If they aren't there, do me a favor, let me know, and I'll put more copies there, because I only put 5 because I didn't think all of the students would want them. And so if you guys want them, I'll be putting them there, and I'll put them in packs of 4 or 5. So then that way you're not having to come all the time to go pick them up, if that's okay with you guys. But let me know, because that's the only way that I know that we're out, because I don't visit every campus every day. So, okay. So how many carbons did we have? I'm sorry, you said 12. I put 12 down here. So we have 12 carbons. How many hydrogens do we have over here?
22.
22. And then how many oxygens do we have?
11.
11. Yeah. And remember, this here just tells us the state. It's a solid. Now, this side here is called the reactants because they're going to be doing the reaction, right? So they're called the reactants. On the other side of our yield arrow, this is called the yield. And then over here, these are called the products. So sucrose, this sugar, is our reactant, and then carbon, and this plus means this and this. So carbon and water are our reactants. Okay? So the plus just means and. Okay? So in other words, we produce carbon and water. Okay? So now this is what we're putting into our reactant. So this is the amount that we're putting into our actants. So the law of conservation basically says that what you put in, you have to get out, right? So what we put in, we have to get out. Our products have to add up to what we're putting into our reactants. So then what we're going to do is we're going to put a number, since we know what this is the chemical formula for carbon, right? So just C is the chemical formula for carbon. H2O is the chemical formula for water. That can't change. Water is always going to be H2O. If we're talking about just carbon, C is always just going to be carbon. Okay? So we can't change the subscripts, but what we can change are, so once we get the formula, we can't change the subscripts. The only thing that we can change is what we call the coefficients. And the coefficients are going to be numbers that we're going to be putting in front of our compounds, our atoms, or our molecules. Okay? So we know that we have 12 carbon here. On this side, right now, since you only have carbon by itself, that means there's only one carbon right now. Okay? Over here, we have H2O. How many hydrogens do we have on our product side?
2.
We have 2. And then how many oxygens do we have on our product side?
1.
Okay, so since there's nothing next to it, we know that that's going to be a 1. Okay, so I'm going to ask you a really hard question now. I want you to think about it for a minute. Are these sides equal? Are our reactant side and our product side equal to each other? So this here is representing our reactant. So I'm going to put a big R by it. And then this here is representing our product. So I'm going to put a P by it. Okay, reactant, product. Okay. Are they the same numbers?
No.
No. So now what we're going to do is we're going to put a coefficient in front of them, in front of the compounds or atoms or elements, so that they will be the same. So what can I multiply 1 by so that it equals 12?
12.
12. So we're going to put a 12 here. Okay, so that now means that instead of having just that one carbon, we have 1 times 12, which is 12. So now we have 12 on our products. Okay, now we have H2O. So we have 2 carbons. So what times 2 will equal 22?
11.
11. So we're going to put an 11 in front of the H2O. Now, This is going to be distributed. By us putting it in front of the H2O, that means that we're going to be multiplying that 11 times our hydrogen and 11 times our oxygen. Okay, so 11 times our hydrogen, so 11 times 2 is 2. And 11 times 1,
11.
11. Okay, so our reactant said that we had 12 carbons. Our product says that we have 12 carbons. Our reactant side says we have 22 hydrogens. Our product side says we have 22 hydrogens. Our reactant side says we have 11 oxygens. Our product side says that we have 11 oxygens. So we have a balanced chemical equation. Okay. You guys, how you feeling?
So it's like you just have to make sure that both sides are equal to each other.
That's right. The quantity on both sides are equal to each other. That is correct. Yeah. And you can't do it by changing the chemical formula. So in other words, we can't change our subscripts. These guys, we can't change those. They're going to be the same. They have to stay the same. We can only put a coefficient in front of them. So, okay. Questions?
So for instance, if there is a reactant that doesn't equal to the products, so it's like if one of them doesn't time each other, so like something like that.
Yeah, so that usually means that there's something wrong. So if your chemical reaction is correct, right? If you know if the formulas are correct, then they should always, what you put in should always equal what you get out. Now, sometimes you may have to have a coefficient in front of your reactant. We didn't have to do that here. So anytime that there's not a number here, it's understood to be just one, right? And so, but it should always add up. If it doesn't add up, something is wrong. Okay.
Okay.
So let's do another one, and then we'll move on to talking a little bit more about those physical changes and chemical changes, okay? Or repeating the physical change plus physical. And then we'll be doing quite a few next week. So. Okay, so we'll do one that's a little harder. So we'll do CH4, and this is a gas. Plus O2. O2 is when oxygen is all by itself, it's always going to be in an O2 form. And that's also going to be a gas. So the oxygen we breathe is O2. And then we're going to make carbon dioxide, which is a gas. And we're also going to be making water. And we're going to have it in its gaseous form, H2O. Okay. Okay. You guys ready to do this? So first off, which side is our product side? Is it the right-hand side or is it the left-hand side?
The right.
That is really weird. So that means the other side is our reactant side. Okay, so we look at both sides and everything, and again, they have to always add up, and they all have to be present. So in this case, we have carbon, we have hydrogen, and we have oxygen. Okay, so on my reactant side, how many carbons do I have?
6.
On my reactant side. So you're looking at the number that's right next to the carbon. What is right next to the carbon?
1.
1, right? So if there's no number next to it, it's always going to be a 1. That's right. Good job, Chantel and Juanita. Okay. How many hydrogens do I have on my reactant side?
4.
Right, 4. And how many oxygens do I have on my reactant side?
2.
Okay, good. Now on my product side, how many carbons do I have?
1.
1. So it's always, we look at it, if there's no number there, it's understood to be 1. That's right. Okay. How many hydrogens do I have?
2.
And how many oxygens do I have? So we
1.
got,
Oh,
oh,
wait,
good.
2.
So we
3?
got 2, we got 3. That's right. So we got 2 with the carbon dioxide, and we have 1 with the water. Okay. Okay, so our carbon is looking good. Our hydrogen doesn't. So what do I need to do?
To multiply by 2 to get 4 equals to each other.
Okay, so we're going to put a 2 in front of the water. So 2 times 2, and that's going to be 4. And then 2 times 1, that's going to be what? 2 times 1?
Mm.
2, that's right. And then we have the 2 that's over here. So 2 plus 2. That's right, 4. Okay, so now we have 4 oxygens. Okay, so our carbons are looking good. We have 1 carbon here, 1 carbon there. We have 4 hydrogens, but now we have 4 oxygens and we have 2 over here. What do I have to put in front of the oxygen over here so that it would be balanced?
Multiply by 2.
Okay, we're going to multiply by 2, and then that's going to give me. Okay, so 4, 4, 4, 4, and 1, 1. Now we have a balanced chemical equation. Okay. Yes.
How do you get to 3 to 4?
How do we get from 3 to 4? Is because when we multiply the water, it's 2 times 1 because there's only 1 water. So that would give us that 2 right here. And then we already had 2 over here with the carbon dioxide. So then that's going to be this 2. So 2 plus 2,
It's 4.
that's how we got it. Yeah.
Okay. Thank you.
And again, this is one of the things that I've picked up over the years. A lot of times we'll pay attention to one and we'll forget about the other. We always have to remember if you have elements in both of them, like the same element in both of them, you have to make sure to count both of them because it's really easy to forget about it. Okay. Okay. So everybody got this down? Got it written down? And don't worry, we're going to do more and you're going to get better as we do more. If you're having troubles, let me know when we start again, and then ask me, stop me, like Jinxie just did, like so that we can make sure that you guys understand where things are coming. Because again, this is going to be something that you're going to be doing throughout the whole semester. Okay? Okay, so again, this is going to represent a chemical change because we're changing the identity. So we started off with the reactants, and then we're able to sit there and change its identity to just carbon and water, right? And so that would be a chemical change. Okay, so now that you know what a physical change is and what a chemical change is, I want you to help me out and answer this. A log burning, a log burning. Okay. So is that a chemical change or is that a physical change?
Chemical.
That's right. It is a chemical change. Now, one way to always know that you have a chemical change is if you can't get the product back. So, can you get a piece of wood back after you burnt it?
No.
No, you can't. Okay. What about an icicle melting?
Physical?
That's right. It is a physical change because you're going from ice to what to liquid water, right? So in that case, it's still the same chemical formula. They're both H2O. So there's no change in the identity of it. Okay. What about a glow stick glowing? So after you break it open, the glow stick, is that a chemical change or a physical change?
Physical change? Because once it stops, doesn't it go back? And then you can do it again?
Can you?
Yeah. Like in the bracelets that you get at the club, you can do that.
Are you sure? Go get because you can get them at the party store
I
or
think it's
sometimes at the 99-cent store, right? I usually get them at the 99-cent store because I'm cheap. So go and get them and break them and then see what happens.
Oh, break it all the way. Oh, no,
Yeah,
you
it's
break it.
can't.
chemical.
Oh, I was thinking just like,
You're thinking about if you break it a little bit, right?
yeah, like if you just snap it, because like that you can. But okay, so then in that case, it'd be a chemical change.
That's right. So it's going to be a chemical change. Yeah, that's right. It's chemical. That's right. Good job, Chantel. Chanel. Sorry, Chanel, right? Not Chantel. My bad. Okay. So how you guys feeling right now? You're feeling confident? Not too bad? Not too shabby?
50-50.
50-50?
Pretty
Okay.
good.
I think we're going to stop here. And so we stopped at physical and chemical change. Put that on my notepad here. And okay, so we'll pick this back up on Monday. You guys have a good 3-day weekend. And then I will see you guys on Monday. If you guys have any questions, I'm here to answer questions.
Wait, so where can you see the previous recordings?
So they're going to be put, let me show you. And as I said, I'll be fixing your both campuses. I'll be fixing your Canvas shell to fix it so that things are popping up the way they're supposed to, so you guys can see everything. So if you go to announcements, and this is going to be on both campuses, I'm showing Kalinga right now. Not announcements, I'm sorry, modules. I'm getting tired. There is a section that is going to say lecture notes. Sorry, lecture notes. That's where you're going to get your notes. and I'll fix it so that 3 is going to show up. So all your lecture notes are going to be here, or they're going to be embedded in the weeks that we're in. Okay. So you'll see them both. They should be in both places. For some reason, the other one, 3, did not go there. So that means it's on the module. If you go to, oh, they're not showing up. We'll fix that. There should be another module that has your videos. And so they'll be here as well. I've been also embedding them in your Canvas shell. There'll be a link, and you click on it, and it will take you to the link itself, and it will take you through the video. And so those videos will have questions that are going to be associated with them. So when you click that link, let me do it as a student. This was the last one. So the new one will be up. When you click that link, you'll be able to see those videos and answer your questions. And they're set up so that, so for you who've already gone through it, you can fast forward through it to answer your questions and get the answer questions. And there's typically like 3 or 4 questions in there. And so those are going to be serving as like your quizzes. Here we go. Okay, so you click here, and then it's going to take you to the video, hopefully. Okay, so here's our video. And so you're able to fast forward through the video. And so, what's my video? Oh, there we go. There's the question. Okay, so what are the components of scientific method? Check all that apply. And so we go through and we answer the question, right? So, observation, question, hypothesis, experiment, results, conclusions. And so then it'll tell you all the ones that are correct and all the ones that are wrong. So then you get your point, and then you continue. So then you go to the rest of your video. You guys can fast forward it to your next one. So since you guys did, okay, so we're going to do this scientific notation. We're going to fill this in. So, I'm going to say, and I'm going to put the wrong answer on purpose. Okay, so it's incorrect. So I continue. And then I can go to my next question. Maybe. So as I was playing through it, right? Apparently, so there are typically 3 or 4 questions in the lectures. And so they're embedded in the lectures. You can since you guys sat through the lecture, you guys are going to be able to fast forward through those lectures. And then just to get to the quiz part of it. So, but like some other students, like right now there's 6 students here and we have 38 students in the class. So in that case, there's quite a few people that have not looked at the lecture. I want to make sure that you guys are watching the lectures. So they're going to be embedded. So make sure you guys get through the full thing. Just fast forward through it and answer the questions since you guys are physically here. But if you want to go back and watch it, you can go back and watch it. It's going to be available for you. We're going to try to get those up on Wednesday, not Wednesday, today's Wednesday, tomorrow. So tomorrow in the afternoon, they'll be up. So you'll have the weekend to go through the questions. The other thing is, what else did I want to say? It'll come to me in a second. So the questions, if you guys have any questions, you guys know that I have office hours on Mondays and Wednesdays at 10:30 to 11:30, and you go to important links. So you guys there to remind you. And this is all my classes, they have important links. So you're going to come here. So you guys already know where the lecture's at. Cocktail hour is going to be 4:30 to 6:30 p.m. via Zoom. So you guys click on there. And so, like I said, I'll be there to sit there and answer questions, or if you guys have any questions about science in general or career choices or anything like that. My office hours, and then Israel's his tutoring hours, and then Angelia's tutoring hours. So make sure that you guys are taking advantage of those things. Angelia is going to be changing hers here soon. She's not going to be doing it on Saturdays. She's going to actually do it one, I believe, on Tuesday morning, and then one, I think it's Sunday in the afternoon as well. So, okay.
Okay. So tomorrow we have a test, right?
No.
No?
I'm glad you asked. No, you don't have a test. So your test has been pushed back. It's going to be pushed back till the 23rd. I'll fix that on the calendar. So you won't be seeing it. And I will actually also open up next week. I'll open up on Monday. I'll open up your practice exam. Your exam is going to be due on the 23rd because Monday is a holiday and I don't want to give you an exam on a Monday. And so, but your practice exam will open up on the 12th. On Wednesday, your exam will actually open up and you guys will have until Friday the 23rd to get it done.